and this would be the concluding session for Python and Biopython as well. So far, we have covered fundamentals of Python, and today we'll be covering a specific library for bioinformatics analysis, that is Biopython. Okay, so I'll now move on to my computer. But by the way, if you have any questions regarding installation of Python or setup or any whatever we discussed in last two sessions, you can ask those questions now, okay, or later as well. So I'll move on to the notebook now. And the link for the workshop material remains the same. I have shared in the chat. So I hope you were able to install the BioPython library. Any issues with that or any questions regarding what all we discussed in previous two lectures? Nothing? Okay, so I hope everything is working fine for you and you are ready. Okay. So today, as you can see, that agenda is to learn about BioPython library, which is for basically analyzing the biological data, be it sequences, structures, or different types of biological data. Okay. Now, before I go into BioPython specifically, I just want to give you an overview of the concept of library. And what is a library and how do we use it when we are working with Python? So let's say if I want to calculate a square root of a number, let's say I say x is equal to 4, and I want to calculate its square root. So I say print, or maybe y equals square x, and then I say print y. Basically what I want to do here is I have some variable, and using that variable I want to calculate the square root, and then I want to print the answer. So if I run this, I get an error. An error is that in line 2 where it says y equals sqrt, name sqrt is not defined. That's the error. So why we are getting this error is because we are trying to use this function sqrt. Again, as you can see, sqrt is a function, but Python in the core Python that you download, and the default Python, there is this function is not there. Sqrt function is not there. But I know that this function is there in NumPy library. There is a library in Python, it's called NumPy. So to use this function, first thing I need to do is import that library. So I call this statement import NumPy. And then I say x, again this x equals 4, y equals, because this function is part of the NumPy library, therefore we have to write numpy.sqrt, then the number for which you want to calculate the square root, and then we can say print y. Now let's run this, and we got the desired answer. So this is the concept, that whenever you want to use a library, you first have to import that library, and then the functions, all the functions or the classes within the library are now available to you to use in your code. Okay, so I hope this makes sense to everyone. Now let's move on to BioPython. So to, again, the same concept, first thing is we need to import BioPython library. And so to import that, we can use this statement import bio, B capital. Okay, and then to check whether everything is working fine or not, or whether the import has been successful or not, you can write this statement print parenthesis open bio B capital dot, this is double underscore. Okay, these are two underscores without any spaces, two underscores version, and again two underscores, then this is close. Now you run this and you should see the version of Biopython. For example, if you have the latest version, it would be 1.79, I guess. Mine is 1.78. So if you are seeing this output 1.78 or 1.79, that means your Biopython installation is successful and you are all ready to go. But if at this point you are seeing some error, that module not found or something else, that means the Biopython library is not installed properly. Okay, so I hope you all could get the version printed on your screens. Okay, so let's move on to the library, some of important functions that are available in the library. So this first we'll start with sequences. Okay, so from to use uh, to process data in Biopython, there is a sequence class. To import that sequence class, we need to use this format from bio.seek. So B capital S capital of seek, import S capital seek. Okay, and from using this function, we can now create a sequence object. So in the next line, I'll just make it like this. So we are creating a new variable. This name could be anything. I'm saying new underscore sequence equals to this sequence, some sequence, AATT, something, anything it could be. So if when I run this, it would create a sequence object by this name, and this sequence would be there. So we can just print this now and see what we get. We get this sequence. When we print the new sequence, we get the sequence. Now you may wonder that what's the need for sequence object. I mean, this could have been done easily using a string also. We could have done some x equals this entire thing, and this would have also given you, if you print x now, x, again the same output. So what's the difference? The difference is in the type, data type. First of all, that's one difference. So if you want to check type of new sequence, what is the data type? Data type of x is of course string. Data type for new sequences, it's a bio.sequence object, while x is string object. So how does this difference matters? This difference matters. So let's clean this up to show you the difference. Now this is our sequence. Now since this new sequence is a sequence object, there are some additional functions available that we can call on this object, which are not available for a string object. For example, this is a DNA sequence, and let's say if we want to find out the sequence of the complementary strand of the DNA, then we can use this function complement. So we say print new underscore sequence dot complement, and that would print the sequence of the complementary strand. You can see that A becomes T and T, A, G, C, and so on. So this is one function available, complement. Similarly, another function that is available is translate. So if you have this a DNA sequence and you want to computationally translate into a protein sequence, then what would be the protein sequence given this DNA sequence? So you can use this function translate, and it would give you the corresponding protein sequence based on the codon table. So if it would take 3 nucleotides at a time and its corresponding amino acid. For example, asparagine, tryptophan, asparagine, leucine, or these 12 nucleotides. Okay, so this is the basic concept of a sequence object. Now, when we are working with sequences, we generally don't have we don't type sequences like this. Okay, we generally read from a file. There is some file, FASTA file or some other file, that we download or get from somewhere, and that we want to read. So you can download an example sequence file from clicking this link. Okay, just right click this link and you can choose save as and save it as kinases.txt. Okay, now, or you can, if you have your own sequence file, that also you can use. Any sequence file would work here. Okay, so now how to read these sequence files and what all we can do with these sequence files. So first, when we want to read a sequence file, we need an additional class, and that is seq.io, sequence input output. So we say from bio, B capital, import seq.io, S capital, IO capital. Okay, and then we say now for, so actually we'll be using seq.io.parse function. There is a parse function in seq.io class. This parse function takes two arguments. First is a sequence file. In our case, it would be kinases.txt, which is available here. And the second argument is the format. Now you can have your sequence file in FASTA format or in cluster.w format or any other format. All you need to do is, you need, if it's, let's say, in cluster.w format, here you have to write cluster instead of FASTA. Okay. So when this parse function works on this file, it generates a list of all the sequences in that file. Now if we have to iterate through this list, we'll use for some variable name. Here I call it all underscore seeks in seq.io.parse and this kinases file and the format, then colon, and in the next line I would say print all seeks dot description. Basically each sequence would have a description and the seek attribute. Now if you are familiar with FASTA format, there is one header which is greater than sign, then some information about the sequence, and followed by the actual sequence. So that header information goes in the description attribute, while the sequence information goes in the seek attribute. So if we run this, we get uh, this kind of output where we have this, or we will see whatever the content of that kinases.txt is there, we'll see it here. So first we have description and then we have sequence. So let's say if we comment out the seek part, we'll get the FASTA header of all the sequences. Okay, or if we want to have sequences as well, then we can have this seek. So this is how we can read a sequence file. Now let's say we want to extract some of the sequences from this file, because there are more than 5,000 sequences in this file, and let's say you want to extract top 10 sequences, first 10 sequences. So how we can do that? And then we want to first of all extract, and then we also want to write it in those 10 sequences in a new file. So how we can do that? So first we'll create a list, an empty list, all seeks equal the square brackets open close. This would create a list called all seeks with no content, or it would be an empty list. Then we'll read this file for, and this statement is pretty much similar to what we saw before, for some variable name seek underscore record in seq.io.parse, the file name and the file format, colon, and this time instead of printing the content on screen, what we'll do is we'll append all these sequences into this list. So we'll have all seeks dot append this variable name seek underscore record. And so once we have done this, and after for loop, we can say print len all seeks. So this would give us the total number of sequences that we have in kinases.txt, because this would be the length and of this list, and this list comprises of each element is one sequence. So if we run this, we get 5489. That means in our kinases.txt there are at total 5489 sequences. Now, as we said, we want to take top 10 sequences and write it in a file. So how we can do that? So for that, in seek.io, there is a function called write. Just like we have read function to reading, the parse function to parse the files or read files, we have write function to write files. Now this write function would take three arguments. First is what is it that you want to write. Second is the file name in which you want to write. And third is the format in which you want to write. So the first part, what is it that you want to write? So we are saying we want to write all seeks, that is our list which has these many sequences. So all seeks, then we put a slice operator. If you remember the slice operator that we discussed in strings, so we say all seeks square brackets 0 to 10. So it would start from the 0th sequence. I mean the numbering starts from 0 and go till 9. So 0 to 9 top first 10 sequences it would take from all seeks, comma. Then we give some file name. So in this case we are giving test.aln. And finally we are giving the format in which you want to save, that is cluster. Okay, so so this statement, the output would be that a new file would get created which would have 10 sequences in cluster format. Let's run this and see what we get. So its output, it says 10. This is basically just to show that 10 sequences have been written. Now if you want to check the output, you can open this text test.aln in a text editor and see the contents. I'll just load here. So this is our new file that we just wrote. It has 10 sequences and the full length, because they are pretty, this is a pretty long sequences. Okay, this is how we can read write files, sequence files. Okay, any questions, anyone? I hope you're doing it along with me and it's working for you. If you have any questions, please feel free to interrupt. Okay, so next part is about multiple sequence alignments, because many times you're not just working with sequences, we are also working with multiple sequence alignments. So how can we work with those multiple sequence alignments? The concept is pretty simple, similar to what we saw about sequences. So we have in bio, we have a library called align.io. Similar to seek.io, we have align.io, and that align.io can be used to read and write sequence alignments. So we first from bio import align.io, then we say align1. This could be any variable equals to align.io, the library, the func class dot read. Again, the same syntax that you want to give a sequence file followed by the format, alignment format. So here this kinases.txt is actually an alignment file, so we can use that, and then the format remains FASTA. So and then so we can just run this part and see what we get. So we got this. So we read this file kinases.txt in a FASTA format, and then we did print align, and we got this thing. So it says alignment with 5489 rows. That means these many are the sequences, total sequences, and 1094 columns. So basically what this means is that we have in terms of number of rows we have 5489, and in terms of number of columns there are 1094. So this dot 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 represents that has skipped some of the columns for the sake of representation. Okay, so now you can think this alignment is like a matrix. where you have rows and you have columns. And let's say if you want to extract certain chunk out of this matrix, you can use the slicing concept. For example, let's say you have this alignment and your region of interest, for example, you want to extract some conserved motif or some ligand binding site. So let's say our motif is this one, this region. This region we want to extract from this entire alignment. So how we can do that? So the concept is we'll uh, create a new variable and let's call it sub underscore alignment. This name could be anything. And then we say this sub underscore alignment equals to align one, our full alignment, and then we write slice operator. Now this slice operator would be slightly advanced from the string operator we have seen, string slice operator, because strings are one dimensional. Okay, this one thing is string, but when we are talking about these alignments, they are two dimensional. So we want to give a slice operator for the rows, and we also want to give slice operator for columns. So the first part will give row range, okay, that what all rows we need. So in this case we are saying colon 10. That means we need the first 10 rows, okay, starting from 0 to 9. So it would take first 10 rows, comma, then we are saying 3 colon 12. Now this is the column slice. So 3 colon 10 would mean 12 would mean it starts from 0, 0, 1, 2, 3. Start at this L or this column, not this L, the entire column, and then go till 12. So 3, 4, 5, 6, 7, 8, 9, 10, 11 till 11. Remember, it's 1 minus the last number. So it would start at this column, go till this column, and for first 10 rows. That is our sub alignment we have selected through this slice operator, and we can check that what our sub alignment. I'll just comment the alignment part and print this. So when we run this, you see this is the sub alignment we got. Instead of the entire alignment, we just got that chunk that we were interested in. So again, as I said, it depends upon what is the purpose of multiple sequence alignment that you have done, and if you want to highlight or extract certain evolutionary conserved motif, this is how you can extract. And if you want to write it in a file, this alignment, you can use this write method, align.io.write sub alignment. Again, the syntax remains the same, that what is it that you want to write? We want to write sub alignment and the file name and the format. So if you run this, it just says 1, and you can now see your msa1.aln file, and it should have this alignment. This is the header information, and this is the actual sequence alignment. So this way it becomes convenient for you to actually use these alignments in your report or publication, because if you have the entire alignment, which is like 5,000 sequences and 1,000, more than 1,000 length, you cannot fit it into one page or one or two pages. But this, if you just want to show a motif for a certain set of, let's say, organisms, this is how you can extract that part, and then you can also use it for making, for example, sequence logos and so on. Okay, any questions on alignment, sequences? Nothing? Okay, so let's move on to the next part, which is running BLAST over internet. So I hope you must have all used NCBI BLAST. So again, let's say if you want to run BLAST through Python or through the program on the NCBI server, so you don't have to install BLAST, you don't have to download any database. But instead of going to the NCBI website, you can, how can you embed the BLAST feature within your program? So that's how we'll see here. So the BLAST library, in Biopython, it's bio.blast, and it has, so here we'll be using two of the functions available in those in bio.blast. First is ncbi www. This is used to run blast on ncbi servers, and then ncbi xml. This is used to parse the blast output from ncbi servers. So the syntax is to import this from bio.blast import ncbi www, and from bio.blast import ncbi xml. Now once we have imported these two, next you need to run the blast. So we create a new variable, we call it result underscore ncbi. This would store the blast results from ncbi, and we say equal to ncbi www dot qblast. So qblast is a function that would actually run the blast, and it takes at least 3 arguments. First is the blast function the blast program that you want to run. For example, in this case, we'll be doing nucleotide blast, so we are using blast n. But if you are doing, for example, protein blast, you will use blast p. Okay, so blast n is for nucleotide blast, and the next argument is the database against which you want to do the blast search. Now here you can specify any database that's available on NCBI servers. I'm using NT, which is a nucleotide database. And finally, the third argument is a GI number, so of the sequence for which you want to do the blast. So basically, this entire statement would be like, it would take this GI number, search NCBI sequence database, and extract the sequence, run blast n against the nucleotide database, and whatever the results of all this would be, they'll be saved in this variable result underscore ncbi. Okay. Any questions? Is there a question?
What's is the meaning of like blast nucleotide and blast protein? What's the
Okay.
real meaning?
So are you familiar with protein sequences and DNA sequences?
Yes,
Yeah. Okay.
yes.
So when you have some protein sequence and you want to search similar sequences to that protein sequence, that is called protein blast. So because we are searching protein sequences, and when you have some DNA sequence and you want to search homologs for that DNA sequence, we'll do nucleotide blast or blast n. So that's the concept of blast n and blast p.
Okay, sir.
And there are some other versions, again depending upon which database you are searching. So I mean that those are, I mean, you can search for blast manual and you'll find those, but basically blast and blast p are used. There are some other also, like blast t, blast x, and so on, where you want to blast a protein sequence against the nucleotide database instead of a protein database, and so on. But blast p and blast n is basically when you input sequence is protein and your database you're searching is protein database, that's blast p. And when your input sequence is nucleotide sequence and the database you're searching is a database of nucleotide sequences, that's blast n.
Okay.
Okay.
Hello,
Yeah.
sir. I
Hello.
don't get this G number, 83321.
Okay, GI number, this is just an example. So if you have a GI number, fine. If you don't have, let's say instead of a GI number, if you have some sequence, actual sequence, not a GI number, so that also you can use here. I'll show you in the next steps. It's there in this tutorial, how to use a sequence file to do blast. But GI number, if you want to search, you can search on NCBI website also. Is that what you're asking? Okay. Okay. Anything else? Okay, so we execute this, the next step would be to save these output, okay, because it's in a variable result underscore ncbi. So instead of working with variable, the first thing we want to do is we want to write everything in a file so that we don't lose that information. So again, yesterday we discussed some of the ways we can which read and write files. There's yet another way to do the same thing. So it's called as with open, uh, and here you'll give some file name that you want to write in a write mode, and as file handle. So instead of doing file handle equals to open, this is with open as file handle colon, and then file handle dot write results underscore ncbi dot read, and then parenthesis close. This basically would write all the contents of results underscore ncbi into this file, my_blast.xml, my underscore blast.xml, because the default format for blast result is XML format. Okay. And with when you're using with option, you don't have to close it because this is like a loop, and as soon as this indentation part ends, it would automatically close this file. Let's run this. This would take some time because because it's running on NCBI server, and you can look at this asterisk part. This indicates that it is executing, and once executing means it is now searching it's now doing the blast search on NCBI servers. So once this is done, this asterisk would change into some number. So let's wait for a few seconds and we'll see it's done. So once it's done, the next step would be to parse this output of the blast that we have just created, my underscore blast.xml. So let's see how we can parse this output. So the first step would be, yeah, any questions? Can you explain this code again? Which code? The blast code? Are you talking about that? Yes, okay. Let me just go back. Yeah. Okay. So the first two lines are basically we are importing libraries, the required classes for Blast, NCBI WW and NCBI XML. Okay. Parse. Okay, parse means to process. Parse means, I mean, if you when you parse data, you basically make sense out of data, or you analyze data in a way that you want to do. That is what is parse means. You read through the data in a defined manner. That is parsing the data. Okay. Sorry. Okay. Yeah. Okay. So next, so these two are we are importing the libraries. Next, this is the actual. By the way, this is done. The blast search is done. The number asterisk has disappeared and some number has appeared. Okay. So this is the main statement which actually runs the blast search. Result underscore ncbi. This is some variable name we create, and this could be anything. Okay, you can just say x or some anything, but just always try to give variable name that makes sense. So result underscore ncbi equals ncbi www. This is the class that we can use to run blast on ncbi servers, and then we say qblast. The qblast is a function. See this, if you remember the syntax of a function is a function. Okay, qblast. So this function needs 3 arguments. So those 3 arguments are, first is the blast program that you want to run. In this case, we want to do nucleotide blast. That's why we are giving blast n. Okay, and the next argument is the database against which we want to search our sequence. So we are giving NT database, and this database could be any database that is available on NCBI. and finally we are giving the sequence which we want to blast. In this case, it would be a GI number for a nucleotide sequence. Basically, this entire statement would run blast search on NCBI site using this sequence against nucleotide database. And this rest of the code is basically we are saving this output in a file, my_blast.xml. We are saving the results underscore NCBI output. Okay. So there are some questions. What if you want to run blast for multiple sequences at a time? So you can do that. I mean, you can just you need to have multiple these statements, multiple such statements. So that also you can do. And does NT refer to nucleotide? Yes, NT is a nucleotide database which is available at NCBI. Okay. Okay, so now let's look at how we can parse this file, or how we can make sense out of this file. This is my_blast. We can target organism. I think that option is there in the QBlast. There all the options that you see on NCBI Blast, for example, which scoring matrix you to use to include organism, exclude organisms, and so on. Those options can be specified as additional arguments here. So you can put some comma and scoring matrix and so on, or organisms. You have to look into the manual of QBlast. So I think those options are there. So you can specify all those things. Okay. Now how to interpret this my_blast.xml. So we'll say result underscore. So we need to open this file first of all. Okay, because we want to read a file. If you remember yesterday's lecture, we have to open a file, and we open this file into this result handler, and then we say blast record ncbi xml dot read this file my_blast.xml. So now our blast record would have all the output of blast. Now this blast record is actually a hierarchically organized output, where you have at the top of the hierarchy you have blast object, and then you have alignment, and then you have high scoring pairs. So to parse this, you'll have to iterate through each hierarchical element. For example, we say for alignment in blast record dot alignments. This is the first list, colon, and then you can print, for example, alignment dot title. What is the title? Whatever is the title of the hit that you got in the blast search. And then you can say for HSP in alignment dot HSPS colon print HSP. If you run this, you get this kind of output. So first you have title. Maybe you can remove this title for now. Run this. So you see this have scores, whatever is the blast score, e value, alignment length, and then the actual alignment. So this is for all the hits that we saw, that we got from blast result. And if you just want, for example, you want, let's say, just e value for all the hits, e value, you can just say print hsp.expect. We got e value. Now, how do you? What is the? What is the advantage of doing all this? Is, let's say you want to have this output, and you want to apply some e value cutoff, and then save only those sequences that fulfill that cutoff criteria. So that we can do easily here. For example, let's say we say with open a new file. We want to write a new file So we call it new underscore file.txt and open it in a write mode as file handler. And then we'll iterate through the blast records like we just did. For alignment in blast underscore record dot alignments colon for HSP in alignment dot HSPS colon. Now we put some if condition. Like we don't print the alignments straight away. We put an if condition that if HSP dot expect is less than this e value is less than some cutoff. So here I have given 10 to the power 105 cutoff colon, and then we write those we print first and then we also write to this file handle dot write and then HSP and then new line character. Let's run this. So first of all we'll see these three sequences in this time, because previously we're getting a lot of sequences in the output, but now we have only three sequences. Why? Because if you look at the e value, all these three sequences have e value less than this cutoff. And similarly it has also written this new file which has again the same content. So this is the advantage when you are working with when you are programmatically doing this blast results, when you're parsing blast results, that you can apply cutoffs or e-value cutoff or similarity cutoffs or any cutoff that you want to apply, and then save those desired results in a separate file. So that's how you can search, do the blast search from Python. Now just to, and now again, if this the previous example was using a GI number. So let's say if you don't have a GI number or an accession number for a sequence, instead you have a sequence. And this example I have given here, the sequence is there. Now how do you run blast with this sequence? So for that, first you need to save this file. You can just copy the sequence and save it in, let's say, any file, for example example1.fasta, and then you say seek underscore file equals open example1.fasta, and then the same qblast statement. Just one difference is there, that first of all this is a protein sequence, so we are using blast p, and then we also need to specify a protein database. So we are saying NR, non-redundant database, which is available on NCBI. You can use any database that is available on NCBI. And then we are saying seek underscore file dot read. This would read the sequences in example1.fasta, and the rest of the thing remain the same. So maybe you can run this, and this is like an exercise that can you figure out from which organism the sequence is, because I have not given any annotation for the sequence. Just copy paste this sequence, save it in a file, and through this blast, can you figure out from which organism is this sequence from? I hope you know the concept of blast, that how from blast we can figure out the organism for a given sequence. Has anyone got it? To figure out the organism, the key part would be this last statement. This when you see the output of this statement, that would give you a hint on what is the organism from which the sequence is from. So let's run this and see what we get. So again, this asterisk means this is running and it will take some time. And then once we have everything done. So what we are basically doing here is we are again saving the blast result in this file, then reading this file, and then what we are saying is print blast record dot alignment 0. That means we are printing the first first hit from the blast result. And if you know the concept of blast, this sequence, if it matches 100% to some sequence in the database, it would be that sequence. That's what we are trying to see. Do we have a 100% match or not? And if we do, that 100% match would obviously be the first hit, the top hit, and that would be the organism it is from. So let's see. Any questions, anyone? I hope you're trying this. This again, this which you mean how to find out organism? Okay. So we have out underscore handle. Where is out underscore? Okay, this one. Oh, this is just a file handler. It's a variable. It could be anything. Out underscore handle. I have just given it. I mean, just a variable name. You can have it anything. So basically, it's a file handler. So just if you remember when you're working with files, you have to have a file handler associated with any file that you write. So we open this file test underscore blast.xml in write mode, and then we have a file handler attached to it, and then we use the write function of this file handler to write the desired thing into the file. Okay, so regarding finding the organism, so we have a protein sequence with us. This is our protein sequence. Now, to find out from which organism is this sequence from, so one thing, simple thing you can try is you can take this protein sequence and do a NCBI blast search against a protein database. So, and if you are able to find a hit which matches to this sequence, that would 100% match. That would indicate that this sequence is, it's the same sequence that is there in the database, and whatever is the annotation for that sequence in the database, that would apply to this sequence. That's how that concept we are trying to use here. It's taking some time. It would run, and then finally you should see some output here. And that out first basically, and when we say blast record dot alignment 0, they are basically printing the first hit or the top hit. Does anyone of you able to run this? Do you have an output? This is not running locally. This is actually running on NCBI servers. So it's actually the speed on those servers that is affecting this execution. Okay, so let's just move on. Let's just wait for this to come. So sometimes, okay, let's say if we have got this output, and let's say we want to pick out the mouse homolog of this sequence. This is not from mouse, I know that. So this, I have some sequence, and I want, let's say, human homolog or mouse homolog of that sequence. So how I can extract that part? So we can do is, we can say for alignment in blast record dot alignments This is pretty similar to what we discussed before. This is continuation to this. I'm assuming that you have run the blast. Okay, we got the result. Okay, so this sequence, the top hit is C. elegans. Okay, this sequence is this MAT protein homolog 3 from C. elegans. So this is how you can check which is the top hit, and you can also check the alignment. It's 100% match. So we know that this protein is from C. elegans. Now, as I was saying, that we want the sequence of the mouse homolog of the sequence. So how we can do that? So once we have done the blast search, it would have all the matching sequences which are there in the database. And if there's a mouse homolog, it should also be there in this blast result. So to get that, what we can do is we can do this for alignment in blast record dot alignments. This is, we are iterating through the alignments within the blast record. This blast record is same as this variable. And then we say if musculus in alignment dot title. Okay, so this is if condition in a slightly different format. So let me just give you an example. So let's say we have some fruits list example that we discussed. Apple, mango. And then let's say we want to check whether mango is there in this list or not. So we can do if mango in fruits, and then print yes, mango is there. But let's say if I write mangoes, and then if I run, let's also put an else part, else. No, it says no because it would match exactly. So basically the concept is the if this thing works is like you have some list, and if you want to check whether a particular element is there in that list or not, you can just say if that particular thing in list. So if I say if mango in fruits, it should say yes. The same concept we are using here, that if musculus in alignment dot title. So if again you want mouse homolog, which is mus musculus. So musculus in alignment dot title. The title is the annotation part. Okay, this title. So, and if this musculus is there, this instead of C. elegans, the name would be mus musculus, or this name would be mus musculus. So that we are trying to see here. If musculus in alignment dot title, then we are saying print alignment dot title, and then we also want to print the sequence alignment that we get from blast. That's how we can print that. So let's run this. So we say first part was alignment dot title. So this first part is that, and we do see a mouse homolog here. And the next part, HSP query 0 to 50. So we are printing first 50 characters of the query, which is our sequence. Then the match, whether it's exactly same or similar. And then the subject, that is the mouse sequence. And then finally we are printing the percentage positives and the scores and the e-value for this alignment. That's how you can parse the blast output and extract the desired components from that output. So instead of going through the entire output, you can programmatically take out whatever information you need from that output. That's the advantage of doing it through program or Python. Finally, here is a way to save all the blast data, blast output in a Excel file, right? Many a times when you do blast on NCBI, I see students taking screenshots of that NCBI website and putting it in reports and dissertations. So instead of taking screenshots, a better thing to do would be to save the blast result in a table or in an Excel file, and then have that nicely formatted thing in your report or whatever you're doing. I'm not able to get out from not which platform. What is the error that you are getting? Which platform? I mean, there's no platform. I mean, is there any output or is there any error that you're getting when you, oh, Google Colab. So Google Colab, maybe there is a problem in writing file. Yeah, so don't you have downloadable, haven't you installed Python locally and Biopython locally on your computer? Because Google Colab is, it's unpredictable. I mean, you have installed, so why not use that? Use your local installation, install Jupyter locally, install Python locally, and then use that. That would make things a lot easier for you to work with. Okay. Okay, going back. Yeah, so this is basically the same thing, and here we are using an additional library, CSV library in Python, that is used to read and write CSV files. Basically, what we are doing here is we create a new variable, CSV underscore out, and then open. We create a new file, blast underscore out dot CSV, and open it in a write mode. And then we want to write, so we can choose what all you want to write. So we are writing, the first thing is, this is alignment dot title. So this is the alignment dot the title for all the sequence, something similar to this. For all, this would be the title for all the sequences. And we are saying split this pipe. So you look at this alignment dot title. This is one pipe, this is another pipe, and this is another one, and another one. So basically, wherever this pipe character is there, it would split alignment dot title. And then we are saying -1. So if you remember the split function, it would split at this character, and -1 means, so 0, this would be the 0th element of the after split, this would be the first element, this would be the second element, so on. So -1 basically starts from the right. So what we would get, instead of the entire alignment title, we'll get this part. So this is actually the this part contains the protein name as well as the organism. So we'll have first this part, and then we'll have the similarity and the e-value. So effectively, once you have run this code, you will get a blast underscore out dot CSV file that you can open it in an Excel, and you will see blast results in a tabular format. That's the advantage, and you can add whatever content you want to include in the table here by just changing this code. Okay. Any questions, anyone? Nothing? Okay, so let me just go back to the okay. So this was all I wanted to talk to you about regarding Python and Biopython. I hope you learned something new from these sessions. And at any point, if you have any questions, please feel free to write to me at this email ID. And if you want to learn more about Python, so you can go to this bioinfo.guru online learning. There's a online learning section there. go to that online learning, and you will see an introduction to Python course. Now, if you want like to enroll to that course, go for self-enrollment and use this key I'm giving you in the chat. Use this key